Hello, and welcome to this overview on uniform circular motion. When you think about it, we spend most of our lives actually moving around in circles. We live on a planet that rotates about on its axis every 24 hours, and we also go around the sun once a year. Circular motion can be used to calculate the speeds that cars can turn bends at and why racetracks are banked. We can look at how circular motion is used to design roller coaster rides, and how to place a satellite in exactly the right place that we need it. But before we can start solving problems, we need to review some terminology and formulae. Well, the first thing we usually want to know when we're solving any motion problems is to be able to calculate how quickly something's moving. If something's moving in a circle, we could, and we quite often do, describe the motion in terms of the revolutions per second or the revolutions per minute. However, in solving physics problems, it's more usual to use the angular velocity, which is the angle turned through over a period of time. In fact, it's the angle turned through each second. Now, of course, we could measure this in degrees. However, we do tend to use radians, which is an alternative unit as an angular measure. Here we have an object moving in a circle of radius r. Now, 1 radian is the angle that is turned through when this arc length here is equal to the length of the radius. This is defined as 1 radian. So when the arc length is equal to the length of the radius, we've got an angle of 1 radian. And so this is a measure of the angular displacement. And so the angle turned through in radians then is found by dividing the arc length by the radius. And so the angle theta can be defined as s over r, where s represents the arc length and r represents the radius. If we now consider one full rotation of the circle, the arc length turned through is going to be equal to the circumference of the circle, which of course is given by 2 pi r. And so our angle that we have turned through now is given by 2 pi r over r. And so the angle turned through in one complete revolution is 2 pi radians. And so we can say that 360 degrees is the equivalent of 2 pi radians. It's useful to be able to convert between degrees and radians, so to convert degrees to radians you just need to divide by 2 pi and multiply by 360, and to convert radians to degrees, divide by 360 and multiply by 2 pi. Now we have an expression for our angular displacement. We can define the angular velocity. As we know, velocity is the displacement divided by the time, and angular velocity is denoted by the Greek symbol omega. Two other useful things to remember that we've covered in the past in waves is the time period, and that is the time for one revolution and is given in seconds. Another useful relationship to remember is the frequency, which is the number of revolutions per unit time and is measured in hertz. And the relationship between the two is that the frequency is 1 over the time period and vice versa. From this we can derive two useful expressions that allow us to calculate the angular velocity. The first one is that we can say that the angular velocity is 2 pi times the frequency, or we can say that the angular velocity is 2 pi divided by the time period. That's just a simple statement of distance divided by time. Now consider a DVD rotating at high speed. So if I put a little blob here and a little blob here, it's clear that they're both going to be moving with the same angular velocity. They're going to be changing this angle by the same amount each time. However, if you were sat on this little blob here, your distance that you have to cover in that time period determined by the angular velocity is considerably less than if you're sat on this little blob on the outside. And so there is a difference which depends on the radius you are out from the centre between another velocity, which we call the linear velocity. Another way to think about the linear velocity is that if you came flying off at a tangent, that is the velocity with which you'd fly off at. Now clearly these two must be linked, and so the equation that links them, if we remember velocity is distance divided by time, we can say that the distance is given by 2 pi times the radius, that's the circumference of the circle at any point, divided by the time period. We know already that 2 pi over t is equal to omega, the angular velocity, and so we can write this useful expression for the linear velocity in terms of omega. And this tells us what we knew already. Basically, it confirms that the further away we are from the centre of the circle for a given angular velocity, the faster we must be moving, which pretty much confirms what we know from common sense. If you've ever ridden on a merry-go-round before, you'll know that the horses on the outside are moving at a faster speed than the horses on the inside. Now let's have a look at some of the key concepts that underpin uniform circular motion. Well, we know for a start off that if something's moving in a circle, there's got to be a resultant force acting on it, otherwise it would carry on in a straight line. Our first job then is often to identify what is providing this centre-seeking force or centripetal force. In the case of the Moon orbiting around the Earth, it's the gravitational attraction that provides the centripetal force. In the case of the hammer thrower, it's the tension in the string. And in the case of atoms, electrostatic forces provide that force that acts inwards. So we've now established that we need a force in order to make something move in a circle. And so if we have a resultant force, then we know there must be an acceleration. But wait, you might think, if I have something moving with a uniform linear velocity, or a uniform angular velocity, how can it be accelerating? Well, remember, velocity is a vector, and so it can be moving at a uniform speed, the magnitude of the velocity vector, but if the direction is changing, which it is if something's moving in a circle, then we know that the force is acting and the acceleration is the change in the velocity vector caused by the change in direction. We can write equations, which I'm not going to derive here, in terms of the linear velocity. It's a is v squared upon r, where v is the linear velocity and r is the radius of the circle. And in terms of the angular velocity, a is equal to r omega squared. Now, we know from Newton's second law that the resultant force is equal to the product of the mass times the acceleration. And so to get from the acceleration to the resultant force, we simply need to multiply each of those terms by the mass. And so that gives us a centripetal force of mv squared upon r, or mr omega squared, both really useful expressions. And there's a reminder of what those symbols mean, where v is the linear velocity, meters per second, omega is the angular velocity in radians per second, and r is of course the radius, and m is the mass. Well, so far we have the following expressions. We can define the angular displacement as the arc length divided by the radius, and since we can define the angular displacement, we can also define the angular velocity, which is the change in angular displacement over time. This is measured in radians per second. From earlier work, we know that frequency is defined as 1 over the time period, where here the time period is the time for one revolution, and so we can say that omega, the angular speed, is equal to 2 pi times the frequency, or 2 pi divided by t, the time period. Still with me? From that, we can link the two ways of describing the speed. We have the linear speed v and the angular speed omega. So the omega is the speed with which the angle changes, and v is the speed of an object which would be actually moving at the outside of the circle or at any point within the circle. So the thing that links the two is of course the radius. Finally, because of Newton's laws, we can define the acceleration for both the linear and angular velocity, and since force is mass times acceleration, this gives us two expressions for the centripetal force, remembering of course that the centripetal force always acts inwards. In the next presentation I'm going to show you some straightforward exam questions for A level using these equations, and then in the presentation after that we'll move on to more challenging questions and real life examples.